Okay, so here is another allowable stress design problem. But this is one where you actually you know all the diameters of the pins, you know the thicknesses of the link, you know all the sizes, and you're trying to find, okay, what's the largest force that I can have here? Okay, so it's a little bit backwards from that last problem in our notes that we did. But we can do this one using the same steps. All right, so using factor of safety of 2.5, calculate the largest force P that can safely apply to the member. We need to make sure that link BC doesn't yield or fail, and we need to make sure pin D does not yield or fail. All right, and it tells us pin D is in double shear. Pin D has that diameter. The thickness of member ACD is 3. The thickness and width of BC is 1.5 inches by 0.5 inches. And tells us the normal yield shear stress of the link, the normal yield shear stress of the shearing shear stress of the pin, and the bearing yield stress. All right, yield stress is really failure stress. We don't want it to yield, so our yield stress is our failure stress. So let me just real quickly, I think you can see if we're going to use the factor of safety of 5, if we know, factor of safety of 2.5, if we know it's going to fail at 75, then I'm only going to allow 7.5. We can do factor of safety equals sigma failure over sigma allowable, or we can just kind of, logically, I think makes sense. 75 divided by 2.5. We're only going to let it get up to 30 ksi. The shear failure stress is 100, so we're only going to allow it to get up to 40 ksi. And the bearing is also a normal stress, so this is the bearing stress at pin D. We're only going to allow it to get up to 20 ksi. So if you have a factor of safety and you're given the failure stresses, you need to find the allowable, what you are going to allow, the stresses you're going to allow. Okay. All right. Now, all these problems, we're still going to have a statics problem. We can look at a free body diagram. We can sum the forces in X, sum the forces in Y, sum the moments. We can solve for some of the forces that are acting at the link. We can solve for some of the forces that are acting at the pin. All right, so let's do that. Here's my free body diagram. I don't think I'm going to redraw this, but here's my free body diagram. I have a pin at D, so I might have a dx and a dy. And this is a two-force member, so I've got the force in member BC, and then I've got that force P right there. I want to sum the forces in X, sum the forces in Y, sum the moments. And when things are, rotated, sometimes you might want to rotate your axes or figure out what axes you want to use. I think I'm going to stick with my usual XY axes. And let me see, do you see right here, let's see, that angle is going to be 30. If we've got this 30-degree angle, that's a 60-degree angle, that's going to be 30 degrees. Might want to know that 30-degree angle so that I can break this force P into its X and Y components. Okay. All right, summing the forces. So this looking free body diagram, remember A, C, D. Summing the forces in X, let's see, would be dx minus FBC. And then plus, let's see, what would be the X component of that force P? P cosine 45, right? Here would be P cosine 45, P sine 45. All right, equals 0. Ugh. Okay, a lot of unknowns right there, but let me continue. Summing the forces in Y. dy minus P sine 45 equals 0. And summing the moments, I can sum moments about any point. I'm going to sum the moments about point D. Okay, so I'm going to say some of the moments about point D, FBC, its perpendicular distance is this distance right here, which would be 12 inches cosine 30. And that would be the way I drew it, creating a positive moment. But then this force P, okay, I could do P cosine 45 in its distance and P sine 45 in its distance. But you really don't have to stick with like necessarily axes for your moment equation. You really just need to stick with clockwise or counterclockwise. All right, see if you follow this with me. I'm going to break this force P into this component, P cosine 15, and this component right here, which goes straight through there. So P cosine 15 is acting a perpendicular distance. Perpendicular distance to this force would be 18 inches, and that would be a negative moment. Do you follow that? You could have done it the other way without looking at these green vectors, just by looking at those pink vectors. But kind of, choosing different ways to break up force P might make that problem a little bit simpler. Okay, what we have, what you're probably going to have for this type of problem where you don't know the force, you don't know the force, and forces are in these equilibrium equations. If you don't know the force, you're probably going to have 4 unknowns in only 3 equations, and we can't just solve right away for all 4 unknowns. We only have 3 equations. But what we can do is we can write everything in terms of this P, write everything in terms of this force P that we don't know. Okay? So I'm going to rearrange this equation, and I'm going to write FBC is, add this to the other side, divide through by 12 cosine 30. Be careful that my units make sense. Everything is in inches. I think this force will be in kips. This is 1.673 P. And so just keep that P, and we'll just move forward keeping that P in our equation, and at the end, maybe we'll solve for P. All right, this equation right here, I can rewrite this. Sine 45 is just a number, 0.707. So I can rewrite this as dy is 0.707 P. I'll box these in, but these aren't final answers. All right, and so then what can I do? Then I can plug that in right there, 1.673. So this is minus 1.673. This is cosine 45 is just a number, 0.707 P. 1.673 P right here, plus 0.707 P right there. I can add those, move those. I've got dx is 0.9659 P. Okay? I boxed those in. I really shouldn't have boxed those in because those aren't my final answers. But I have done the best I could to get the forces that are acting at the pin and the force that's acting in member BC. And I'm going to write those in terms of P and then move on. Okay? All right, so if it's a problem like this where you don't know all the forces, you're not going to have enough equations to solve for everything right away. So you're still going to have one variable, this force, that's in your equations. Okay, so now I need to test for, and sometimes we might call them failure modes. I need to test for the ways it can fail. Test for, all right, what do I want to start with? I can start at the pin, I can start at the link. I'm going to test for failure at link BC. I'm going to test for failure at link BC. How might BC fail? BC might fail due to normal stress failure at BC. Okay. I've already told that I'm only going to allow the normal stress in BC to get up to 30 KSI. All right. I know that normal stress is N over A. So I know I'm going to let it get up to 30 KSI. What is the N inside link BC? It is this force BC, 1.673 P. And what is the area for the normal that the normal force is acting over? It's the cross-sectional area of that link. That link is not a circular link. That link is a rectangular 1.5 inches by 0.5 inches. 1.5 inches by 0.5 inches. And from that, you can get a force P. Right? You can get a force P of 13.45 kips. Okay, I'm not going to box that in because that's not my final answer. That is the force. Let's write this down. This is the force at which link BC will fail due to normal stress failure. Okay, I'm going to put a star by that and come back to that. Okay, now I need to test for other ways it could fail. Maybe before the link fails, maybe the pin has already failed. So I want to kind of see what fails first, or see what fails at the smallest force P. That makes sense, right? All right, so let me test for failure at pin D. It kind of told us we need to make sure that link BC doesn't fail and make sure that pin D does not fail. Let me test for failure at pin D. How might pin D fail? Well, pins definitely might fail due to shear stress failure. Okay, but pins also can fail due to bearing failure, and I was told the bearing failure stress at pin D. So I need to test for shear stress failure and bearing stress failure. Okay, so first, let's think about shear stress failure. Let's think about shear stress failure. Actually, before we do that, let's think about what force is acting at pin D. What force is acting at pin D? What force is acting at pin D? Both dx and dy. Right? Both dx and dy. And you can still square these and take the square root. 0.707 P squared plus 0.9659 P squared, take the square root. And I've got a force at D. I still have that P. I can do something P squared plus something P squared, take the square root. I've got 1.197 P. That is the force at pin D. Okay, anytime you have a pin and you've got like a dx and a dy, square those, take the square root to get the magnitude at pin D. All right, that's the magnitude at pin D. Let's make sure it doesn't fail due to shear. Let's make sure it doesn't fail due to shear. Shear stress is V over A. The shear stress that I'm going to allow it to get up to previously is 40 KSI. The V, all right, what is the V? Is the V just that 1.197 P? Well, the pin, it doesn't show a side view. It tells me pin D is in double shear. So the V that it's acting is 1.197 P divided by 2. All right, and the area that shear stress occurs for pins is the circular cross-sectional area, pi by 4 diameter. I was told the diameter 1.25 squared. And from there, I can find force P. I get a P of 82.01 kips. All right, so let me put a star by that and say this is the force at which pin D will fail under shear. That's the force that it will shear off. You know, that's the force that the shear stress reaches over and above the maximum allowable force that I'm going to allow. Okay. Then I need to test one more failure, and that's bearing stress failure. Bearing stress failure. So bearing stress failure is really a normal stress failure. And I was told, let's don't let it get above 20 KSI. The end that's acting is this same 1.197 P, and it is not divided by 2. It doesn't matter whether we're in single shear or double shear. The force at the middle, let me kind of look at a side view here. If this is our pin, and here's the link A, or not link, sorry, but here's member ACD. Then the shear stress would be divided by 2, but the bearing stress is this force right here. That force is going to be the full 1.197 P. All right, so anyway, don't divide when you're doing bearing stress failure, don't divide the force divided by 2, even if it's in double shear or single shear. All right, so divided by the area. The area for bearing failure, do you remember in the notes where we took this pin and we cut it in half, and this would be the bearing area. So I took this right here and I cut this in half, and I want to find this area. This dimension would be the thickness of member ACD. Right, that would be the thickness of member ACD, which was 3 inches. It told me in the problem statement this is 3 inches. And then this distance right here would be the diameter of pin, which is 1.25 inches. So this is 1.25 inches by 3 inches. Okay. Up here, the area that shear stress occurs is a circular area of the pin, but right here, the area that bearing stress occurs is the rectangular area if I slice the pin in half of this middle section where it might be crushed. Okay, so from that, the only unknown is P. I can solve for P, and I've got a P of 62.65 kips. All right, I'm not going to box that in. I'm going to put a star by that, and I'm going to say this is the force at which pin D will be crushed, will fail due to bearing failure. Or, you know, it's not going to fail because of that factor of safety, but that's the force that makes the bearing stress up to its maximum. Okay. Now, very, very important. You've got to look at all your failure modes. You've got to look at all the ways it could fail. In this case, there were 3 ways that it could fail. It could fail because pin D fails due to bearing. It could fail because pin D shears. Or it could fail because the link fails due to normal failure. We need to answer the question, what is the largest force P that can be safely applied? What is the largest force P that can be safely applied? Now, it might seem counterintuitive, but do you see that we need to choose out of these 3, we need to choose the smallest. We need to choose the smallest because once you apply anything past 13, it has already been broken. The figure is no longer in static equilibrium. So it will never get up to this 82 for the pin to fail because the link has already failed. It'll never get up to this force 62 kips because that link has already failed. So it might seem counterintuitive, but you got to choose the smallest force P. So the maximum P that we're going to allow is 13.45 kips. And I'm going to box that in. And maybe I'll make a note. Link BC is the limiting factor. Link BC is the limiting factor. All right, let's take a minute and review this problem. This was a problem where we knew all the dimensions of the pins, we knew the size of the link, we knew all the sizing. We didn't know what force could be applied, what maximum force could be applied. All right, so we write our static equilibrium equations to try to solve for all the forces acting at the pins, acting at the links. Anywhere that could fail, we need to kind of find the force acting there. But in this case, we couldn't really just find a force. We found a force that had P in it. It still had this variable P in it. That's okay. We just carried that variable throughout our problem. Then we looked at all the different failure modes. This could fail due to normal stress in the link, so I found the force at which the link will fail. This could fail due to shear stress at the pin. I found the force that the pin will shear fail. And it could fail due to bearing at the pin. So I found the force that will cause bearing failure at the pin. And then I decided, okay, I cannot go above 13.45. 13.45 is my maximum allowable force. Link BC is the limiting factor. For these problems, I'm going to want you to show all your work. You've got to show and calculate correctly what force it will fail, the pin will fail, what force the link will fail, and if I tell you something or ask about bearing failure, got to calculate the force that bearing failure will occur. Choose the minimum, and that is your maximum force allowed.